Welcome to the Explainer. Okay, let's dive right in, shall we? If you are a focused learner aiming to completely, absolutely master the Cambridge A-Level Physics Waves chapter, you are in exactly the right place. Seriously, this isn't just going to be another quick review or a boring read-through of a textbook. Think of this as your ultimate strategic blueprint. Today, we are going to demystify exactly how progressive waves transfer energy, we'll break down the core mathematics you actually need, and most importantly, we're going to equip you to spot and sidestep those incredibly sneaky exam traps that catch so many students out. So get comfortable and let's get started. Here is our roadmap for today. We've got 5 key stages. First, mastering wave fundamentals. Second, equations, speed and intensity. Third, wave types and motion. Fourth, decoding the Doppler effect. And finally, number 5, polarization and Malice's law. Starting right off with Section 1, Mastering Wave Fundamentals. Okay, so the absolute most foundational concept you need to have locked in your brain is that progressive waves transfer energy from one place to another without actually transferring matter. The energy moves across the room. The particles, they just stay put and vibrate. Now, with that established, here is literally the #1 trap that students fall into on exam day. You flip the page and you see 2 graphs that look almost identical. Just a bunch of squiggly sine waves, right? But hold on, check the horizontal axes. It's a total game changer. The top graph is displacement against time. This is tracking one single lonely particle over time, and the distance between its peaks gives you the period, or t. The bottom graph, though, that's displacement against position. It's like taking a photograph, a snapshot of the entire wave in physical space at one specific millisecond. On this one, the distance between the peaks gives you the wavelength, or lambda. If you mix these two up, your calculations are going to be way off before you even really start. And honestly, this brilliantly illustrates our first major takeaway, coming straight from the examiner's study tips. They say, it is easy to confuse these 2 graphs. Check the axes carefully. You know, top grades don't actually start with doing complex, mind-bending math. They start with simply taking a breath and reading the graph axes before you rush to write your answer. Moving on to Section 2, equations, speed and intensity. Beyond just the basic wave speed equation that we all know, you really need to wrap your head around intensity. By definition, intensity is the energy transmitted per unit time per unit area at right angles to the wave velocity. If you want to visualize it, think of it simply as the power per square meter. But here is the absolutely crucial rule for your exams, like underline this twice in your notes. Intensity is always proportional to the square of the wave's amplitude. It's an exponential relationship. This means if you have the amplitude, the intensity doesn't just halve. Oh no, it decreases by a factor of 4. When you eventually encounter those tricky ratio questions involving amplitude and intensity, and trust me, you will, remember this very clear warning. As the textbook notes, there are no simple formulas you can apply here. You need to ensure that you understand the physics and then work through in a logical fashion. Seriously, don't just blindly plug numbers into a calculator hoping for the best. Mop out the relationship logically step by step. All right, Section 3, Wave Types and Motion. So we know energy is moving, but what are the particles actually doing physically as the energy passes through the medium? Well, there is a fundamental split here. On one side, we have transverse waves. Think of water ripples on a pond or light. In these, the particles oscillate at right angles, meaning perpendicularly to the direction of the energy transfer. On the flip side, we have longitudinal waves, like the sound of my voice right now. Here, the particles vibrate back and forth parallel to the energy transfer. This parallel motion creates areas where the particles are all squished up together, which we call compressions, and areas where they are stretched out, which we call rarefactions. Now, how do we actually analyze these invisible sound waves in a laboratory? Well, we use a classic setup featuring a cathode ray oscilloscope, or a CRO. It's basically a monitor for waves. A microphone picks up the longitudinal sound wave and feeds it into the CRO, which translates it into a visual display on a screen. By looking closely at the time-based setting on the scope, you can easily determine the period of the wave, just counting from one peak to the very next. And once you have that period in seconds, finding the frequency is a breeze. You simply calculate it as 1 divided by the period. Let's do a quick mental check right now, based on the source text. Imagine a train engine bumping into a long row of stationary trucks, sending a mechanical shockwave pulse all the way down the line. What do you think? Is this model transverse or longitudinal? Think about the motion for a second. The trucks are knocking horizontally, back and forth, entirely parallel to the direction the pulse itself travels down the track.
Because of that parallel motion, this perfectly models a longitudinal wave.
Let's jump into section 4, decoding the Doppler effect. This is one of the coolest parts of physics, where relative motion literally bends the rules of what we observe. Have you ever been standing on the street and noticed how an ambulance siren sounds really high-pitched as it races towards you, but the second it passes, the pitch drops and sounds way lower? That's the Doppler effect in action. When the source of a wave is moving, the wavefronts literally bunch up in front of it. They get squeezed. This gives the wave a shorter wavelength and consequently a higher observed frequency. But behind that moving source, the waves are stretched out much further apart, which gives them a longer wavelength and a lower observed frequency. To actually calculate this phenomenon on an exam, we use the Doppler effect formula. It looks a bit intimidating, but it's really not. The observed frequency, which is f0, equals the source frequency, fs, multiplied by the wave velocity, v. Then you take all of that and divide it by v plus or minus the velocity of the source, which is vs. But wait, here is exactly where students consistently lose easy marks: the sign conventions in the denominator. Let's lock this logic in right now so you never forget it. If the source and observer are moving towards each other, a minus sign is used in the denominator. Why? Think about the math. A smaller denominator results in a higher overall frequency, which matches our ambulance analogy. Conversely, if moving apart, a plus sign is used, resulting in a larger denominator and therefore a lower observed frequency. If you remember the logic behind it, you will never mix up the signs. Now, while sound waves are cruising along at just a few hundred meters per second, electromagnetic waves are a entirely different story. Every single one of them shares the ultimate unbreakable speed limit in a vacuum, c, which is exactly 3.00 times 10 to the power of 8 meters per second. And that constant speed brings us beautifully to the electromagnetic spectrum. We're talking everything from tiny, incredibly energetic gamma rays with wavelengths of 10 to the negative 16 meters, all the way up to massive radio waves, stretching up to 10 to the 5 meters. What's absolutely vital to remember for your exams is that while they all travel at that identical speed of light c in a vacuum, their vastly different wavelengths dictate entirely different real-world properties. Gamma rays will penetrate and ionize, while microwaves will cause water molecules to resonate and heat up your dinner. The properties shift gradually, hand in hand, as the wavelength changes. And finally, Section 5, Polarization and Malice's Law.
Okay, we are entering one of the more complex, abstract areas of our blueprint, where we actually force light oscillations to restrict themselves to a single plane. Unfiltered, normal light is chaotic. It vibrates in all directions. But passing it through a polarizing filter, that restricts those vibrations to just one single straight plane. It's like sliding a frisbee through the slats of a picket fence. We call this plane polarized light. Now, if you take that nice, organized plane polarized light and hit a second crossed filter, meaning a filter that has turned at exactly a 90-degree right angle to the first one, it will block 100% of the light. Nothing gets through. It goes completely dark.
Here is a vital conceptual anchor you absolutely need for those tricky multiple-choice questions. Ready? Longitudinal waves cannot be polarized. Think about why. Because they vibrate parallel to the direction of travel, a filter just can't physically block their plane of oscillation. Sound waves do not care about your polarizing filters. Therefore, if a wave can be polarized, it is definitively 100% a transverse wave. No exceptions. But what happens if that second filter isn't at a perfect 90-degree angle? What if it's just slightly tilted? Well, that's where Molice's law comes to the rescue. It mathematically states that the final transmitted intensity, I, equals the original incident intensity, I0, multiplied by the cosine squared of theta. And what's there? It's simply the angle between the light's original plane of polarization and the new filter's transmission axis. So, let's test your exam mastery right now. A plane polarized beam hits a filter at exactly a 40-degree angle to its transmission axis. Grab your calculator, plug 40 degrees into Molice's law, and square the cosine to find the exact fraction of the original intensity that actually makes it through. Actually doing these calculations and proving it to yourself is exactly what turns a good student into an exam master. But before you go, I want you to think about this real-world application. If we can entirely block light with a simple 90-degree turn of a polarizing filter, how might brilliant engineers use this exact physical principle to design the LCD screens of the devices we stare at every single day? It's all connected. Keep questioning the physics around you, keep practicing those graphs, and I'll see you in the next explainer.